Hello, today we are going to do a worked example. We have looked at diffraction, we have looked at reciprocal space. So, many of those concepts we are now beginning to become familiar with. So, we are going to look at a worked example which relates some of the theory that we have discussed with something that you may actually do experimentally, which is to obtain diffraction patterns and then try to analyze those diffraction patterns. So, that is something that we as materials scientists we do quite often in the lab, and one of the tools that we use quite regularly these days is the electron microscope. So, we are going to see how what we have calculated relates to a diffraction pattern that you would obtain off of a electron microscope. So, in fact, we are going to actually generate a diffraction pattern, and if you actually had a sample, it would generate a pattern similar to what we are going to put on the board. Okay, so, that is the activity that we are going to do. So, I will put down something like a question, then we will look at various aspects of the question, and in the end as we finish off we will have a pattern which is the diffraction pattern that corresponds to that question. So, let us put down the question first. Okay, so, the question is this: we want to generate an electron diffraction pattern, in this case a spot pattern, because we will assume it is a single crystal. We want to generate an electron diffraction pattern for an FCC crystal for the zone axis 0, 1 bar 0. Okay, so, there are a lot of things that are specified here which maybe you may not have been familiar with or to some degree you may have familiarity with. So, I will walk you through some of the terms and then we will actually do the pattern calculation, and then so we will go about it. So, the first thing I want to point out is this term. So, there are a lot of things here. First is that I am talking of electron diffraction pattern. So, there is some reason why I am indicating that. I am talking of a FCC which means face centered cubic crystal. So, that also has some significance in the context of the question. And the third thing that is of importance is this concept that it is along a particular zone axis. So, the issue is this: when you take a single crystal and you obtain a diffraction pattern from it, that pattern is going to differ based on how the crystal is oriented with respect to the radiation that is incident on it. Okay, so, that is why the zone axis comes into being. Okay. And the diffraction pattern that you get will also depend on the manner in which the diffraction pattern interacts with the crystal, and that is why I have spoken about electron diffraction. So, that I will briefly indicate, and the fact that it is a face centered cubic crystal also puts some additional specifications on it. So, first let us start with something called the zone axis. So, you may already be familiar with it. I will just very briefly show you what we are referring to when we say zone axis. So, basically we simply say that supposing you have a plane. So, I will just draw a plane, and let us say another plane intersects it. So, naturally when two planes intersect, if they are not parallel, they are going to intersect at some point and they will intersect along some line. So, I will put that line down here and we will just say that this is another plane. Okay. So, we now have two planes which are intersecting each other and they intersect along this line. Okay. So, now as you can imagine, when you have a line that is on a plane, then the normal to that plane is going to be normal to that line. So, anything that is perpendicular to this plane will automatically be perpendicular to any line on that plane, because that is how the plane is defined. You have a plane, does not matter in which direction you draw lines on that plane. If you have a normal, that normal will be normal to any of those lines, right. So, this line lies on this plane, it also lies on the other plane. So, on both the planes this is a common line. So, therefore, this line is perpendicular so if I draw the perpendicular to this plane, it is roughly in this direction. Okay. So, that is perpendicular to this plane here, this normal that I have drawn here, that is also going to be perpendicular to this common line. Similarly, if I take this plane here, the normal to it will be some in this direction, and that naturally will also be perpendicular to this line, because this line is common to this plane as well as this plane. Okay. So, therefore, when you have two planes intersecting, the line of intersection is perpendicular to the normal of each of those planes, right. So, this line, this common line is then referred to as the zone axis, and you can actually have multiple planes, you can have a series of planes which go through this line. So, you can have several planes going through this line, common line, or at least you can find such planes which are all going through this common line, and for all of those planes this common line is referred to as the zone axis. And in inverse way of saying it, all those planes are said to belong to this zone, they are planes of this zone. Okay. So, it is a direction, it is a line in a crystal lattice. So, you can specify it as saying UVW, you will say, you will specify a line in the crystal axis as UVW. So, that is how it will end up coming, and it is a specific line. So, you have square brackets here. So, therefore, you will find that when you specify this, you can say, you can look at all the planes that are perpendicular to it, and they will belong to this particular zone. So, that is this UVW that we are referring to here in this particular question as 0, 1 bar, 0. Okay. So, this is the zone axis that is there. Now, why we have picked the zone axis is something we are going to look at in a moment. But at the moment, this is what we are referring to as zone axis. I have just indicated to you two planes, and I have shown you the normal to it. Now, we will keep this picture in mind, we will come back to this in just a moment. What I am going to now draw is just a set of points which would then represent points in reciprocal space, and I will also draw the evolved sphere. In this case, it is 2 dimensional, so an evolved circle, so to speak, which is the condition that we have identified as our diffraction condition. So, let us just draw some points here. Okay, so I have a 4 by 4 grid. Okay, let us just put one more point, 5 by 5 grid, let us just do it. So, let us say these are points in reciprocal space, they are points corresponding to a reciprocal lattice which corresponds to some real lattice. Let us not worry about which real lattice it is, these are valid reciprocal lattice points. So, we discussed in our earlier classes that so we would designate something as the origin, which would then be 0, 0, 0, and if we have some radiation which is interacting with this lattice, we would draw the a vector which would have 1 by lambda as its magnitude, 1 over lambda as the magnitude, and the direction would be, it would just contact this 0, 0, 0. And then you would draw a circle with this as the center. So, you would get a circle of this nature, and wherever it happens to touch a reciprocal lattice point. So, for example, in this diagram the way I have drawn it, it seems to appears to touch this reciprocal lattice point. So, then the condition for diffraction is satisfied for this reciprocal lattice point with respect to this radiation in this crystal. So, that is how we have seen it. So, this is a large, this is a circle that I have drawn. Now, the point to remember is one additional detail we will add here, which is that as I mentioned once before in one of our earlier classes, you have a choice here. You have a crystal which belongs to the sample. So, naturally you can keep changing from sample to sample, and therefore, you can have different crystals corresponding to them, a different array of points would appear here. You could also have, independent of the sample, you can have different radiations incident on it. For each radiation the wavelength would differ. Okay. So, therefore, you can actually independently vary the radius of this circle. or a radius of the sphere, in this case a circle appearing as a circle on 2 dimensions. You can independently vary this sphere, and therefore, for a given combination of crystal and wavelength of radiation incident on it, specific set of points would satisfy the Bragg condition, would satisfy the diffraction condition, right. So, that set of points is going to vary as you change the wavelength. It is not the same regardless of the wavelength. So, it is going to come based on the wavelength that you put on. So, that is one point that we need to keep in mind. But there is sort of an extreme end of this picture of this basic concept that I have shown you, that you can have a small circle, you can have a larger circle, even larger circle and so on, based on the wavelength. And it is sort of an inverse picture, because the larger the wavelength that you are putting incident on the sample, the smaller is its reciprocal quantity. So, this 1 by lambda becomes smaller and smaller as your actual lambda goes up. The opposite happens as you keep decreasing the wavelength. This radius keeps becoming larger and larger of this circle. So, it becomes larger and larger. Normally, for example, in X-ray diffraction, you will have wavelengths of the order of, say, approximately in XRD, X-ray diffraction, you will have wavelengths of the order of, say, 1.5 angstroms, of that order. So, copper K alpha is roughly in this dimension, this kind of quantity. The interplanar spacing is also of the order of 2 angstroms. Approximately 2 angstroms. If you go to electron diffraction, what happens is the wavelength that we use in electron diffraction so this is lambda here, lambda is approximately 1.5 angstroms. Lambda is of the order of something like 0.0, say 0.01 angstroms or 0.02 angstroms and so on. Okay. So, what happens is, so you see these numbers here, you have a 1.5 angstrom, you have a 2 angstrom and you have a 0.01 angstrom going to electron diffraction. I mentioned to you that these are what you are plotting in reciprocal space is an inverted quantity, right. So, if it is large in real space, it is small in reciprocal space. These two quantities are similar. In real space, you have 1.5 angstroms, you have 2 angstroms. They are a similar order of magnitude. So, you will see a set of points here, and the spacing between these points, which will be the inverse of this interplanar spacing, you are plotting the inverse of it. So, this is say if it is 2 angstroms, the interplanar spacing here is the interplanar spacing in real space. In this reciprocal space, it will be 0.5 angstrom inverse. So, that is what it is going to be, right. In reciprocal space 1 over 2, so that will be 0.5. So, I will just say that this is 0.5 angstroms inverse. So, that is the dimension of this quantity in reciprocal space. The 1.5 angstroms would be inverse. So, that is actually going to be in a similar order of magnitude here. So, if you do, so it will be roughly about 0.6, 0.7 angstrom inverse. So, that is also of the same order of magnitude. So, you will have a radius of that order. So, 1 over 1.5. So, roughly approximately 0.67 angstrom inverse. So, little larger than this 0.5, so something like that. So, you see when you use X-ray diffraction, the radius of the evolved sphere that you generate is very similar in magnitude to the interplanar spacing that is present in the crystal. Okay. So, that creates a certain type of set of interactions that are possible, and as you change the wavelength, you start seeing different points in the different points satisfying the Bragg condition. However, when you go to electron diffraction, you are using wavelengths that are 2 orders of magnitude different from the interplanar spacing, right. So, if you have a wavelength of 0.01 angstroms, the when you do the incident wave vector, this is the incident wave vector which has the magnitude 1 by lambda, that 1 by lambda, that incident wave vector is now of the order of 100 angstrom inverse. The modulus of your incident wave vector is of the order of 100 angstrom inverse. So, it means if you have only 0.5 here, so you have to go 200 spacings along this line, 200 spacings along this line before you can put the origin or the center of the sphere, right. So, right now for example, I have put it at little over 1.5 for this particular wavelength you would get. For XRD you would see something like this. That is notionally okay, may not be an exact thing. So, that is the center here. So, that is the sphere with the center here corresponding to the wavelength 1.5 angstroms wavelength. Okay. So, that is for X-ray diffraction, this would be the center, and with respect to that you would have this wavelength. Some other wavelength which would be slightly smaller would have a little larger wave vector and would generate that sphere that we originally drew. What I am telling you is that when you use electron diffraction, you are not going to go the center is not going to be just 1 or 2 reciprocal lattice vector spacings. You have to go 200 times, 200 spacings along this line before you reach the center. Okay. So, you will have to go very far, very far on this board. So, you probably will have to exceed this board well past this the length of this board before you reach the center of the Ewald sphere corresponding to the wavelength of 0.01 angstroms. Okay. So, but that does not change the condition for diffraction. The condition for diffraction is still the same. The condition of diffraction for diffraction simply states that whenever the Ewald sphere touches a reciprocal lattice point, diffraction will occur, right. So, that condition of diffraction simply means that you have to now generate the sphere corresponding to 100 angstrom inverse, okay, 100 angstrom inverse, and wherever that happens to touch a reciprocal lattice point, you will see diffraction. As you can see here, so given this condition, as you can see here, when I go from a smaller radius to a larger radius, the curvature starts decreasing, right. So, that is inversely related, curvature is inversely related to radius. The smaller the radius, the more curved it is, larger it becomes less and less curved. So, if you go to larger and larger and larger radius, it almost starts becoming planar in the scale of this diagram, right. So, a larger radius would look something like that. So, some larger radius. So, these are the reciprocal lattice points. Okay, so, those are reciprocal lattice points here. So, I have now drawn a part of a sphere which is larger in radius than even the one that I originally drew. So, if you continue this, what normally happens is that when you go to electron diffraction kind of conditions where you have 100 angstrom inverse as the modulus of the wave vector that you are putting in, the sphere corresponding to it in the scale of this diagram will almost look like a flat plane. It is a huge sphere of which you are seeing only a small section, and in the scale of this diagram it looks like a flat line, I mean it looks like a straight line or a plane in this if you look at it in 3 dimensions. It is simply the surface, a small section of the surface of a very large sphere in the scale of this diagram, okay, because the radius of this sphere is 200 times the spacing away, and therefore, in this scale of this image it looks like a flat straight line. So, that changes or that brings in certain very interesting situations into this analysis. The main thing that it brings in is the fact that these are all now in this these reciprocal lattice points that it intersects have a special property. You can see that corresponding to, so basically I am only going to draw a part of this incident beam wave vector. So, that is going to be something like this, and it continues, okay. So, that is your incident beam vector, it just continues quite a bit, like I said 200 spacings that side. So, I am only drawing part of it. Here this wave vector, as you can see from the diagram that we have drawn, is perpendicular to this direction that you have here. It is actually basically perpendicular to this plane, and of which we are only seeing a 2-dimensional section. So, you are seeing a line. So, therefore, all of these vectors that you see here, this is one vector, this would be another vector, These are all vectors that are going from the origin 0 0 0 to specific reciprocal lattice points. Okay. So, though all of those vectors are actually perpendicular to this vector that you see here, and this vector, this long vector is your incident beam vector. Okay. So, what do we observe? So, the main points that we observe are, when you use electron diffraction, the points that satisfy the diffraction condition appear to lie on a flat plane, in the scale of this diagram, and they are all points that are perpendicular to this incident beam direction. Okay. So, and what are these points? They are reciprocal lattice vectors. And what is the property of a reciprocal lattice vector? It is perpendicular to a plane in real space, and the magnitude of it is the inverse of the magnitude of the interplanar spacing, right. So, we wrote HHKL is perpendicular to HKL, and modulus of HHKL equals 1 by DHKL. These are the things that we wrote, which is going to hold true, does not matter what your lattice is, etc. So, these are reciprocal lattice vectors. So, therefore, they are naturally perpendicular to those respective HKL planes, and their magnitude is 1 by the spacing or 1 over the spacing of that particular HKL plane. Now, let us go back to our previous diagram. You see here a perpendicular, you see another perpendicular. So, you automatically see that these are these can naturally represent directions in reciprocal space, correct, because they are perpendicular to respective planes. So, this is perpendicular to this plane, this is perpendicular to this plane that I have drawn here. Therefore, they are valid reciprocal lattice directions in reciprocal space, and if the magnitude is 1 over the spacing of the planes in this direction, then that would be a vector that would lead to a point in reciprocal lattice. But the interesting thing here is that they are all perpendicular to this line here, that is the zone axis. Okay. So, we have reciprocal lattice vectors, directions of reciprocal lattice vectors are perpendicular to the zone axis. First, we independently drew this. We had two planes intersecting. We said that the line that intersects that is common to them is the zone axis, and we also noticed that the perpendiculars to each of those planes are naturally also perpendicular to the zone axis. Now, we also recognize the fact that these perpendiculars to those planes happen to be the directions in which the reciprocal lattice vectors would be for those particular planes. Therefore, we recognize that the reciprocal lattice vectors would be perpendicular to the zone axis, right. Now, let us go back to this figure here. We have a series of reciprocal lattice vectors, and they are all perpendicular to this one line. Therefore, this one line coincides with the zone axis corresponding to these planes. In other words, if I were to take this picture and go back to that picture here, this is the beam direction, right. This line that I am saying, this line is commonly perpendicular to all of these points, all of these vectors. This is the beam direction, and these are reciprocal lattice vectors. So, this image, if I move it to this picture here in real space, this is your beam direction. So, that is the direction of the beam, and that coincides with the zone axis, and then you have all the reciprocal lattice vectors which are now perpendicular to it. They would now correspond to points which in the reciprocal space, and that is how you would see it. So, therefore, when you take electron diffraction, the pattern of points that you see represent points of a zone. They are all vectors which belong to that zone axis, and the beam direction coincides with that zone axis. So, that is the important point that we wish to note. Okay. So, that is the peculiar thing about electron diffraction, and how it shows you the points that you see there which are spots, those are all spots corresponding to the same zone, right. So, now let us go back to this problem we have here. So, we understand the significance of electron diffraction in the context of this question. We also understand the significance of the zone axis, which means this is the direction in which the beam is coming, 0 1 bar 0, and corresponding to that we also have an FCC crystal for which in the 0 1 bar 0 direction the beam is incident, and corresponding to that we want to generate the diffraction pattern. So, we will now do that there. Okay. So, we will now take the zone axis here again, zone axis is 0 1 bar 0. Couple more concepts we will put in here which are very interesting. I also mentioned here it is FCC. Okay. So, what I am actually going to do is actually I am going to generate the reciprocal lattice points corresponding to this zone axis actually for a simple cubic. Initially I am going to do only for a simple cubic, then I am going to put a condition which says that certain of those points corresponding to simple cubic are not allowed for face centered cubic. So, you remove those points, what remains is the diffraction pattern of the face centered cubic. These are called extinction rules. There are something called extinction rules simply because in a face centered structure you have additional atoms at some locations which lead to additional cancellations or additional destructive interferences, and therefore you will get a set of points if they were simple cubic, but some of those points get cancelled when you have face centered cubic. Another set of points get cancelled when you have body centered cubic or body centered structure. Body centered structure, face centered structure, you have some cancellations going on, additional cancellations. So, a simple cubic structure in this case will give you the superset of points that you can get, and a subset of those points is what you will see in face centered cubic, another subset is what you will see in body centered cubic. Okay. So, we will do it for simple cubic, then we will eliminate or we will highlight those points which are now valid for FCC. Specifically for FCC, the condition that holds for a point for diffraction to be displayed by a plane or a set of planes is that the H, the K and the L values should either be all odd or all even, should be all odd or all even. In this context they also instead of saying all odd or all even, they simply say unmixed, meaning either all odd or all even. So, a 2-2-2 plane can give diffraction, a 2-4-2 can give you diffraction, 2-4-0 can give you diffraction, but a 2-4-1 cannot give you diffraction, 1-0-1 cannot give you diffraction, things like that. Okay. So, that is the problem. In the case of simple cubic, such restriction is not there. Any value of HKL potentially can give you a diffraction pattern. Okay. So, potentially can give you a diffraction pattern. So, when we first draw the spot pattern, we will draw for simple cubic. We will not worry about the individual values of HKL being unmixed, odd or even. Then we will identify from that set only the ones that where HKL are either all odd or all even, and for that we will generate the, that subset is then the diffraction pattern for the face centered cubic structure. So, this is the zone axis. When something is a zone axis, the planes that belong to this zone, so zone axis we will designate as UVW. The zone, so that is the zone axis. Any plane HKL belongs to this zone if HU plus KV plus LW equals 0. So, this we will not derive here, we will simply accept this. There are derivations for this available, you can look it up, but this is straightforward relationship. So, if HU plus KV plus LW equals 0, then that HKL plane belongs to this zone. Okay, and therefore, it has it has a line, this axis actually falls on that plane like you saw for those two planes earlier. So, now if you look at our zone axis that we are considering for this problem, we have 0, 1 bar, 0. So, if I take any arbitrary HKL plane, what I am saying is h times 0 is 0, 0 minus k plus 0 should equal 0. If I just do HU plus KV plus LW equals 0, so you have 0 minus k plus 0 equals 0. So, therefore, for this to be equal to 0, we simply are requiring that k should be equal to 0. Okay. So, all planes where k is equal to 0 belong to the basically belong to this zone axis. Have this as the zone axis. Okay. So, I can write all these planes. So, therefore, quite simply if I have a 1 0 0 plane, it would belong to this zone axis, or the zone would belong to this zone, and I could also have 0 0 1 plane that would also belong to this zone, right. So, all of these would belong to this zone. Now, having so normally in reciprocal, like since it is a vectorial, it is a set of points that can be obtained by vectorial addition. it is sufficient if you obtain 2 points with something as the origin, and then you can the 2 closest points to the origin, and from there you can get all the other points simply by doing a vectorial addition, which is what we are going to do. So, but to do that we need both the dimension, we also need the angle between those 2 points. So, to get the angle, when you have H1, so this is H1 K1 L1. So, this is one plane that belongs to this zone, for which that is the zone axis, and this is H2 K2 L2. So, the angle between those planes is simply H1 H2 plus K1 K2 plus L1 L2 divided by square root of H1 square plus K1 square plus L1 square multiplied with square root of H2 square plus K2 square plus L2 square. So, this is what we will get, and this is cos of the angle between, so this is cos theta equals this, right. So, now I have those 2 quantities there. So, if I just do this H1 square plus K1 square plus L1 square, square root of that is simply 1. So, square root of 1 square plus 0 square plus 0 square, that is square root of 0 square plus 0 square plus 1 square, both are square root 1. So, I essentially have 0 plus 0 plus 0 square root of 1 into square root of 1 equals 0. Therefore, the angle between those 2 vectors is 90 degrees. So, cos theta is 0, so therefore, theta is 90 degrees. So, therefore, I can set something as the origin, and I will just draw, so basically the first point that I put down here, I can declare as let us say I declare this as 1 0 0. So, I will call this 0 0 0, this is 1 0 0, and so this vector 0 0 0 to 1 0 0, the other vector has to be 90 degrees to this. So, I will just take a perpendicular point here, a direction perpendicular to it, and I will call this 1 0 0 0 1. Okay. And now with these I will just draw a 5 by 5 grid, and we will just name all the points. So, I will just put here point here, a point here, and okay, 5 by 5 grid. We will just stick to, we will just stick to 5 by 5 grid. So, you have these 2 points here. So, we will just do that. So, square grid of 5 by 5 points. Okay, so, I have a 5 by 5 square grid just drawn on the board. We will just name the points. So, we have 2 points already identified here, 1 0 0 0 0 1. So, we can just name the other points. So, this would be a vectorial addition of these 2. So, this is 1 0 1, right, and this is I move 2 steps in this direction. So, this is 2 0 0, this is bar 1 0 0, this is bar 2 0 0. Similarly, this is 0 0 2, this is 0 0 bar 1 in the negative direction, 0 0 bar 2, then we can name all the other points. So, this is 1 0 1 bar, this is 2 0 1 bar, so this is 1 0 2 bar and 2 0 2 bar. So, we can continue this. So, this is 1 on the, so this is 2 on the x direction. So, 2 0 1, 2 0 2, this is 1 along this direction, but 2 along that direction. So, this is 1 0 2. Okay. So, similarly this would be bar 1 0 1, this is bar 1 0 2, this is bar 2 0 1, bar 2 0 2. Okay, and we will finish these 4 points here. So, this is bar 1 0 bar 1, this is bar 2 0 bar 1, this is bar 2 0 bar 2, and bar 1 0 bar 2. Yes. So, that is what we have. Okay. So, the first number that you get will be the extent to which we are moving in this x direction. So, minus 1 minus, so this is all minus 1, this is all minus 2, and this is all 1, this is all 2, and the last number that you get is the extent to which we are moving in the up and down direction. So, all these numbers end with 1, all these numbers end with 2, all these numbers end with bar 1, all these numbers end with bar 2. So, this is how we have got the set of points. So, these are all the points, please remember these are all the points without any further restriction, all the points without any restrictions on H, K and L. I have not put except that they are all the points that correspond to that zone. Okay, so, they all belong to this zone. So, zone axis for all these points is 0 bar 1 0. So, that is the only restriction that is there on. So, I have taken a cubic lattice and identified all the planes that belong for whom this is the zone axis, and I have plotted them in reciprocal space. And please remember that the only thing that I have not, the directions are correct. The only thing that I have not specifically put a value to is the length of that spacing. So, just for our simplicity's sake, we will assume, just so that the numbers are convenient for us, but it does not really, we will say that it was the interplanar spacing there was let us say it was 2 angstroms. That is the example that we used there, I think, yeah 2 angstroms is what we used. So, therefore, all of this is 0.5 angstrom inverse, 0.5 angstrom inverse. So, that is all it is. So, we have got the dimension also is now correct, and the direction is correct, because this is supposed to be 90 degrees. We found 2 directions, we found 1 0 0 0 0 1, and we said that we found that the actual angle between them is 90 degrees, and therefore, we went ahead and built up this entire system. So, right. So, we have got all the points that belong to this zone, and the dimensions are correct, the directions are correct. So, therefore, this is the set of points which are likely to be, which are the points basically that are on this line here. This is a line here, in reality this should have been a plane, and that is why the same plane I have now turned around and I am showing you that plane there. So, this is the plane that is like this plane that is on this coming out of the face of the board going into the face of the board, that same plane I have put it flat on the board, and that is what you see there. That is the set of points you see there. So, corresponding to that diagram, your beam direction is perpendicular to this board. So, the beam is falling on the sample like this, and those are all the points that are possible, right. There you had the beam coming from, beam is coming from here, and that is the plane, beam is coming from here, that is the plane. I have just turned it around, beam is coming from here, this is the plane, and that is what you see there. So, that is the thing that you see. Now, additionally I told you that so we have satisfied several things here. If you go back to our question here, we said electron diffraction. So, wavelength is very small, therefore, the inverse of the wavelength, the wave vector is very large. We found out the zone axis, we understood the meaning of the zone axis, and therefore, we were able to identify all those points that belong to that zone axis, and we also found out that when diffraction occurs using electron diffraction, the points that you see are all the points that correspond to the zone axis. So, those points lie along this line, those are all perpendicular to the beam that is coming in. So, that also we have done. So, all these parameters we have taken into account. Only thing we have not yet accounted for is the fact that it is a face centered cubic lattice, right. So, for that face centered cubic lattice, the additional condition that I told you is here. In the case of a face centered cubic lattice, for diffraction to occur, in addition to the fact that those planes have to belong to that zone when you are using electron diffraction, in addition to that condition, we want H, K and L to be either all odd or all even, right. So, now in our case, we are forced to look at only all even, because we have got K equal to 0, that is the condition that we got for the planes to be in that zone. So, since K is forced to be 0, and so it is 0 in all the points that we have identified, we are forced to look at only the condition that all even is what is going to get permitted for this particular combination of beam direction and sample. Some other combination you could have got all odd also. So, in this particular case, because the beam direction is like that, you have k equal to 0, and therefore, we are only looking at all even points. So, what are all those all even points? We can just see here. So, this is 1 odd, 2 even. So, it is not going to give you a diffraction spot. This is all even. So, this will give you a diffraction spot. So, I will just circle it. So, that is going to give you a diffraction spot. Similarly, if you come here, all even is here, this will give you a diffraction spot, this will give you a diffraction spot, diffraction spot, diffraction spot, this one here, this one here, and this one here. So, you now suddenly see that out of that full set of points that a cubic lattice would have given you, a specific subset is what the face centered cubic lattice will give you. Okay. So, this collection of points, this layout of points that you are seeing here, if you take that layout of points, that will be the diffraction pattern that you will see when you do the diffraction of a face centered cubic crystal with the beam aligned such that it is lining up with the 0 1 bar 0 direction. So, this is what you see as your diffraction pattern, and this is how it relates to what all the things that we have discussed in terms of reciprocal space and so on. So, the reciprocal lattice points that you generate are directly related to the diffraction pattern that you see, and that is what we have shown, I have shown you today. So, this is what happens. The only additional detail that we have not put into this is the scaling. I have put the actual value here of 0.5 angstrom inverse, but as you can imagine, any diagram you draw, you can simply magnify this, or it's a scale that you draw. So, right now let's say this is 4 inches across. I have simply on this board I have said 4 inches equal to 0.5 angstrom inverse. You can simply say 2 inches equal to 0.5 angstrom inverse, in which case the whole thing would shrink a bit, or you can expand it a bit. So, that is like any other you're magnifying or decreasing the magnification kind of thing. In the context of diffraction pattern, we talk of it as camera length. You can change the camera length, and that changes the extent to which these points spread out or come closer together, but the layout of points, the angular layout of points would be exactly the same, okay, and the pattern that you would see would look exactly the same, right. So, this is how it relates. So, this is a example that I wanted to work you through. So, anytime you are given a particular lattice and you are given the beam direction as something that coincides with the zone axis, a particular zone, it becomes the equivalent of a zone axis in that particular crystal. It lines up with the zone axis in that crystal. Then corresponding to that, you can generate the diffraction pattern. The steps that would be involved are, of course, first of all, as just to summarize here, the steps that are involved is using the fact that the beam is coming along a particular zone axis, you identify, so that is UVW. If any particular HKL has to belong to this, what would be the condition that would be required? Mathematically, this is the condition that has to be satisfied. So, given you have a particular value of zone axis, you have to figure out what are the restrictions on HKL for it to belong to that zone. Okay. So, for example, I could pick another example where, let us say I am looking at, I will give you another value here, which would be let us say the 111 direction. So, supposing you had a 111 direction, then you would require basically a particular value of H, K and L such that the values work out to be 0. So, if you have, so for a 111 direction, for example, if you were looking at 111 direction, so the two planes that would then, two nearby planes that would satisfy this would be a bar 1 0 1 and a 0 bar 1 1. These two planes, if you put in this zone axis, you will get, you will be able to satisfy a 0. So, the first thing is you figure out at least two planes which belong to the zone axis, which are the nearest set of planes that you can think of, the smallest indices planes that you can think of that would satisfy this condition for that particular zone axis. Then you also, it is important to figure out what is the angle between those two planes. In our case, it conveniently turned out to be 90 degrees. So, that is why you have a square layout of points there. If in this particular case, for example, it will not turn out to be 90 degrees. So, if you actually did this formula for it, so H1, H2 would be 0, K1, K2 would be 0 and L1, L2 would be 1. So, you would have 1 and so this is cos theta, and the square root of H square plus K square plus H square would be square root 2, square root of H square plus K square plus L square would be again square root 2. So, this would be root 2 times root 2. So, this is 1 by 2. So, theta is actually 60 degrees, cos 60 is half. Okay. So, if I had this as the zone axis, the two planes that I would pick would be these two, which would be very close. From experience you can pick the lowest indices planes that would satisfy this condition of belonging to this zone, and they would belong to this zone because they would satisfy this equation, and then I also need to know the angle between them. So, I should, instead of drawing a square set of planes points that I have drawn here, I would set something as the origin, I would set something as the 1 bar 0 1, and then at 60 degrees to it I would set the other one 0 1 bar 1. So, those two I would set at 60 degrees. So, this would be twisted 60 degrees, then I would generate all the points. After having generated all the points, I would then look at this additional condition, the extinction condition, which is whether they are all odd or all even, and then generate all of these points. The subset, identify that subset which then satisfies the all the conditions required in that problem. Okay. So, this is a nice worked example that I thought I should share with you, which shows you how you go from a reciprocal lattice calculation to a diffraction pattern that you would actually see, observe under an electron microscope. So, next time you see a diffraction pattern, you need not be worried, you can relate to a lot of the things that we have discussed in our class, and it will easily tell you how they relate to each other. In all this discussion, there is one other point that I thought it would be interesting for you to keep in mind, and that is simply that, you know, when you talk of real space and reciprocal space, any quantity that is large in real space becomes very small in reciprocal space, and vice versa. So, that you have already seen. I mean, so a very small wavelength becomes a very large wave vector, and correspondingly, you know, relatively larger interatomic spacings become relatively smaller quantities in reciprocal space. So, what you see here is actually a slice in reciprocal space that you are of points, and these are points now because we are talking of a large single crystal where the dimensions are all large in all dimensions. Supposing instead of a single crystal, large single crystal, you had a thin film. So, by definition a thin film is very small in one dimension, is very large in two dimensions, right. So, corresponding to it, the intensity that you will see if you talk in terms of intensity of a spot in the reciprocal space, it actually becomes a rod. So, where it is in large in two dimensions, it becomes small in that dimension in reciprocal space, another small thing in a reciprocal space. Where it is thin, it becomes a long rod. Okay. So, that is something that you can at least keep in mind. You do not have to immediately, I mean, to do this you do not immediately need it, but just for you to, you know, really relate the thing that you see in the electron microscope to what you draw here. When you see variations in intensity and so on, those are some of the parameters that impact the variation in intensity. And also you are taking a slice, so exactly where it slices through reciprocal space will give you, that is why when you tilt the sample a little bit this way, that way, you will start seeing changes in intensity and so on. And those are all the things that impact the intensity. Okay. So, we will not get into that detail too much, but this is how what you have, all the things that you have discussed relate to what you will actually see in an experiment. One other point that we should also note is that the origin, the choice of origin is arbitrary. So, in fact, the origin is also a point that would satisfy all of our conditions, which is that the h, k and L are all even for our particular problem, because you have the 0 0 2 bar point here. This could have been chosen as the origin, then that would have been satisfied as the corresponding point. So, this then would be the final layout if you looked at the FCC, with that being the zone axis. So, with this we will halt today, and we will see in some other class. Thank you.